Hello everybody, and welcome to the first part of this tutorial series that I am calling RGBA. This tutorial series is geared towards beginner game developers, and in this tutorial series, we are going to be discussing using images and pixels as data sources. So, an important concept to understand when you're starting game development, or even 3D graphics or graphics in general, is that computers only understand numbers. So everything you see on a computer screen is a representation of a number. And using this knowledge, we can begin to understand that images are really just data sources. So how can we use images, and how exactly are they data sources? An image on a computer is basically a two-dimensional array, basically meaning a collection of values. And it's two dimensions because we have an x-axis and we have a y-axis. So for example, this image, this representation of an image is a 7 pixel by 7 pixel square image. And each one of these pixels, basically each one of these grid spaces, holds a value. And in fact, it doesn't hold just one value, it holds 4 different values. So what exactly do I mean by that? Well, if we take a look at this texture here, and don't worry if this texture looks confusing, I'm going to show you exactly how this texture works later on. But essentially, we have a 2048 by 2048 texture. So we have 2048 pixels on the x-axis and 2048 pixels on the y-axis. So when you multiply 2048 by 2048, you get the number of pixels in this image. And for each one of these pixels hold 4 different values. And basically that means that we can treat pixels as 4-dimensional vectors. If I sample a pixel here, if you pay attention to this part of the screen right here, when I sample these pixels, you can see all these values changing. Now, I said earlier that pixels store 4 different values, but you're actually seeing like 8 values here. Well, in this tutorial series, we're not going to be covering the hexadecimal value or the HSV values, and that's because really these values hold the same information as the RGBA values, but in a different sort of context. We're only going to be paying attention to the red, green, blue, and alpha values, because we can directly extract these values in any game engine or in any piece of software, because really these values are what's directly stored into image formats. So as I'm sampling all these different pixels here, you can see these values change. So for this last pixel I selected, we have a red value of 244, we have a green value of 134, we have a blue value of 255, and we have an alpha value of 26. So you can start to understand exactly how we can, these numbers are existing, so somehow we can use these numbers to our advantage. So going back here, we have a red value, a green value, a blue value, and an A for alpha value, RGBA. And we have these 4 values for every single pixel in a texture or in an image. So what is one way we can use this knowledge to our advantage? Well, the first topic we're going to be discussing in this video is channel packing textures. So to give you a brief rundown of what the history of channel packing is that during the beginning of the sixth generation of home consoles, being the GameCube, the PlayStation 2, and the Xbox, the original Microsoft Xbox, consoles were opened up to more dynamic lighting effects. One very common method of dynamic lighting back then was specular highlighting. So back, for example, in Halo 2, what they would do is that they would take their typical color texture like you see here. We have a metal, rusty metal texture. And what they would do is that they would take a grayscale image, which would represent the intensity. So for example, this image, let's just say this is the specular map. They would take a grayscale image that would represent how strong or how weak the specular highlight on a model was, and they would pack that into the color texture, into the alpha channel of the color texture, because most of the time the alpha channel is not being occupied by any data. So that was one way to reduce data redundancy, or just data being spread out into different sections. Essentially, it helps with optimizing basically the complexity of your project. Another benefit to this is that instead of having to load two different textures into memory, only one texture had to be loaded into memory. Basically, that one texture acted as two different textures, but only one texture needed to be loaded in, so that really saves on memory as well. The PBR worlds, the physically based rendering world that we currently live in, texture packing is, in my opinion, not only beneficial, but it is necessary. For example here, and if you want to follow along, the texture I'm using for this video is from ambientcg.com, and I'm using Metal Plates 13. I would recommend downloading the 1K PNG or 2K PNG. I'm using the 2K PNG. So here, when you download it, you get all these different files. Now, the two files you're not going to get is this ORM and ORMD. We're going to actually be creating these textures in this video, but you'll get, important for this video, you'll get an ambient occlusion texture, the base color texture, displacement, metalness, the two normal maps, and the roughness texture. So when we make PBR materials, so when you're working with PBR materials, usually you're going to be working with 5 different textures. You're going to be working with an ambient occlusion, a color, a metalness, a normal map texture, and then a roughness texture. Let's go ahead and let's go into Blender and let's see exactly what this PBR material looks like. Here I have a monkey head with a subdivision surface modifier applied to it. And you can get it here, add mesh, monkey. I shaded it smooth as well, and I gave it the default material. So here we have a principled BSDF node, and principled BSDF node is basically Blender's version of a PBR shader. Let's bring in the color map, and let's go ahead and let's plug that into base color. You don't see anything change because that's because we need to go into viewport shading. And now we can see our color texture, but it doesn't look very interesting. It doesn't look very realistic. And that's because we only have the color map. So next, let's bring in the metalness texture. And let's plug that into metallic. And now we're beginning to see a bit more visually interesting texture. Next, let's bring in the roughness texture. Let's plug that into roughness. And now you can really start to see, the metal parts are reflective and the rusty parts are not. And finally, let's bring in the normal GL texture. And let's plug that in. Oops. Let's plug that into normal. And wow, that looks terrible. It looks just confusing. And that's because we did a couple things wrong just by plugging the normal map directly into the normal slot here. First of all, we need to get a normal map node here. And what this normal map does is that it takes the values, kind of like what we just discussed earlier. It takes the pixel color values of a normal map and it converts it to a 3D, basically a 3D vector for each pixel. So let's take the color and plug it into the normal map, and let's plug the normal map into normal. It still doesn't look right. It looks better, but it doesn't look right. And that's because we are treating this texture that is storing data. We're treating it as if it was an image we would be just looking at, like a typical image. But this is an image that's being used as a data source. So we need to change color space here from sRGB. We need to change this to non-color. And immediately it starts to look a lot better. And we can actually do the same thing with the metalness texture and the roughness texture here. Since these are basically data sources, we can change color space to non-color for the metalness texture, and roughness texture, we can change that to non-color as well. We don't want to change it for the color map because the color map is meant to be viewed, like the pixels on that map are meant to be part of a visual format, but the rest are basically data format. One other texture I forgot to bring in is the ambient occlusion. Now, the principled BSDF node actually doesn't have an option for plugging in ambient occlusion. So what I do is that I get a color mix color node, and I set from mix to multiply, and I just bump up the factor to 1. I plug in the color texture here into A, and then the ambient occlusion map into B. And then I'll plug in the multiply into base color. So now we do have our ambient occlusion map. And again, because this isn't really being used necessarily as a data source, the ambient occlusion map, we can keep that as sRGB. Our PBR material is finished. We have a monkey that has rusted metal on it. It looks pretty good, looks pretty realistic. But you'll notice here we have 5 different textures loaded, and you might start to realize, especially depending on how much bigger your project is getting, that you start running into performance issues. We don't really need all 5 of these textures loaded into memory individually, because that's really going to slow things down for us. So what is one way we can kind of compress this data into, less resources essentially? Well, that's when we start to get into channel packing. So if I get my, textures back here, you'll see that 2 textures you did not get when you downloaded these textures is that you didn't get an ORM and an ORMD texture. And that's because these are textures that I've created that I channel packed. And if I bring this in, if I bring the ORM texture in, ORM is a specification. It's an acronym. It stands for occlusion, roughness, and metalness. For example, if I go into the Godot engine here and I want to create a new material, you'll see here under base material, we have ORM material and we have standard material 3D. We're going to get into this later, but essentially all you need to know is that ORM and standard material are almost identical. The 2 materials just handle the texture files you give it differently. So ORM, you can see here, uses an ORM texture. Now, really, you can channel pack your textures in any way you want to, but ORM is a common method if you use software such as Substance Painter or Armor Paint. From my understanding, those softwares will automatically export an ORM texture. And you can see here that Godot supports ORM textures right out of the box. Unreal Engine also supports ORM textures, and I believe Unity does as well. How do we utilize this ORM texture? Well, I'll show you in Blender. Before I do, let me explain exactly what goes on in an ORM texture. So let me open it up. Actually, let me open up a new instance of Blender. And let me show you what's going on here under the hood. So I'm going to open up a compositing tab, and I'm going to just bring in this ORM texture. So if I plug the image into composite here, and in fact, I'm going to get a viewer node. I'm going to plug in image there, and you can see the ORM texture. Like I said before, we can use the red, green, blue, and alpha channels to store values. So what happens if I get a color mix separate color? I plug this in here. And what if I take the red value and just plug that into viewer? Now we start to get something quite visually different. And you'll notice, let me change color management to standard here so it looks even more accurate here. Let me zoom out, and let's compare that to our ambient occlusion texture. Wow, that looks pretty much identical, and that's because it is. Let's take the green, let's put that into the viewer, and that looks identical to our roughness map, and that is because ORM is a specification of channel packing where you store the ambient occlusion texture into the red channel, the roughness texture into the green channel, and then the metalness texture into the blue channel. But how do we compress 3 different textures into just one texture? Let's take a look at the roughness texture. Let's start sampling these pixels, and you can see we get all these different values here, but the RGB values are identical. So really, we kind of have redundant data here. We don't need 121 stored in 3 different places. That's just completely redundant data. So that's how we can pack 3 or 4 different textures into just one texture, by taking the grayscale value, which is going to be identical, and instead of storing it into all 3 or all 4 values here, we can just store it into one value. Let me open up the ORM texture here just to show you. Let's sample the very first pixel, top left corner of this image. You'll remember that in ORM texture, the roughness channel is stored in the green channel. So if we sample this pixel here, we should expect 104 on this one. And we do, that's what we get. But you can see here it's stored in all 3 different places. But here we only needed to store that information on one pixel, or sorry, not one pixel, one value of the pixel. This is what channel packing is all about. You take data that's already redundant anyway, and you pack it into one source where you no longer have any redundant data. And that really saves on memory, that really saves on, it doesn't necessarily save on storage, but it does save on just memory, on how many textures you can have loaded in at one time, and stuff like that. How PBR materials work, let's take a look at the roughness texture. Kind of like how I said earlier when we were discussing specular maps on old Xbox or GameCube or PlayStation 2 games, where the wider a pixel is, the greater the specular highlight is on that particular part of the texture, versus the darker the area the pixel is, the less intense the specular highlight is on the part of the texture. And PBR materials work in the exact same way. So if we take a look at the roughness texture here, you can see we have areas that have lighter pixels and areas that have darker pixels. And in the context of a roughness map, what that means is that the wider a pixel is, the more rough that area of that texture is going to be. And the darker a pixel is, the more shiny, the more reflective that part of the texture is going to be. Now, one thing I want to get across very clearly in this video is that channel packing is not just limited to specular maps or PBR materials. If you're using a texture as a data source, you can pack that texture. It doesn't matter what it is. If, let's say, you're not even going with a PBR approach for your game, or maybe you are going for a PBR approach in your game, but let's say you want to add different special effects to your materials. So let's say you have an asset that you want to share across a snowy level and a kind of a dusty, sandy level. Well, you can create a texture mask that tells the material where to apply sand or snow onto the material. It would be a grayscale image essentially, and you could pack that grayscale image into another texture somewhere. So again, it's as long as you're using an image as a data source, you can pack that image. So for the sake of example, let's say if you're making what I just said earlier, a texture that applies snow onto a material, you can say, okay, this part of the texture right here that's black is going to have no snow on it or no sand on it, but the white part of the texture is going to have sand or snow on it. And that's basically how it would work. And you can see, since this is a grayscale image, we have values that are redundant, that are shared across the RGB values. And for that, because of that, we can pack that texture. So how do we get to actually packing these textures? How do we go from a roughness texture and ambient occlusion and metal texture to an ORM texture? Well, as I said earlier, from my understanding, I haven't used these softwares before, but Substance Painter and Armor Paint will generate an ORM texture automatically for you. Let's say you're not using those programs, or you want to take a more manual approach. Well, I'll show you one way you can channel pack your textures. And we're going to be using Blender. So earlier I showed you that in the compositor here in Blender, I brought in a separate color node, and you can see that we're getting our textures back that I've packed into this one texture. But since we can separate colors, we can also combine colors together. So let's get a color mix combine color node, and we can delete the separate color in this ORM texture here. So let's plug this into the viewer node. Let's bring in our ambient occlusion texture, our roughness texture, and our metalness texture. Let's bring those in. You can see that the ambient occlusion, when we put that into red, we start to get this red texture. Let's bring in our roughness. There we go. Now it looks like a red wall covered in mustard. And let's bring in our metalness texture, and let's put that into blue. And you can see we get our ORM texture right here. We just packed our texture. But let's export this. I'm going to put combine color, I'm going to put this back into composite as well, because when we render and save this texture out, it's going to be looking for this input going into the composite node. Now, one thing we need to do, first of all, I would highly recommend you go here under the properties panel, you go to render properties, the render properties tab, you scroll down until you see color management. You want to change view transform to standard. If this is set to AGX or filmic, you're not going to get accurate values. You want to change this to standard, and you can see how these view transforms are changing the values here in our texture. We want the values in our texture to be accurate. So let's set this to standard, and that's going to give us our accurate textures. Now let's go to the output, and we need to specify, if we just render this out right now, we're not getting our whole texture. And that's because we are rendering at a resolution of 1920 by 1080. So we want to change this resolution to the resolution of our texture, which is 2048. Now, one more thing we need to do is under post-processing, we want to put dither, we want to change dither down to 0. What dither does is that it adds extra noise into the image. And we do not want extra noise added to our image because that is going to alter the values that are stored in the pixels of our image. So we don't want extra noise. Change this dither value to 0, and that's going to get rid of the extra noise. Now we can render this out, and we can go to image, save as, and I am going to save this in my textures folder, and I'm going to save this. I saved it. I basically made an identical name, but instead of like metalness at the end, I replaced it with ORM. I would highly recommend you save this in PNG format. Now, I don't know about the limitations of Unreal Engine or Unity or other game engines, but except for HDR images or EXR images, any other image except those formats are limited to a color depth of 8. So if you're saving this as 16, you're adding a whole bunch of information that's totally useless, specifically if you're working in the Godot engine. And let me show you a big difference here. So every single one of these textures, if we take a look at all of these textures, we can look at the size. So this ambient occlusion texture is 482 kilobytes. This color texture is 5.82 megabytes. Which we can kind of expect because, you know, a color texture is going to have more data than a grayscale image. Well, if we take a look at the displacement map here, despite being a grayscale image, it is 5.65 megabytes. That's pretty huge for a grayscale image, and let's see why. So I'm going to open the properties of two different images here. I'll take the ambient occlusion. And let's look at the details panel. Here under image, we see our dimensions, but bit depth is 8 for the ambient occlusion, and the displacement map, it has a bit depth of 16. Basically what that means is that each pixel has, if it's a 16-bit, it has a higher precision than an image with a bit depth of 8. If we take the roughness map here, which is an 8-bit texture, and we sample any pixel, that pixel is going to be between a range of 255 and 0. So basically, that pixel can store 256 unique values. A 16-bit pixel can store more than that. But typically, 8-bit is fine. 8-bit's being used in every texture except the displacement texture. Even the normal map texture is, I believe, 8-bit. Wow, okay, never mind. It has a bit depth of 48. If you're working in Godot Engine, you may want to, I would open this normal map up into Blender, put that into the compositor render, and then save this out as an 8-bit image. And this can be saved as RGB. There's no alpha channel, so I would say this is RGB. And I'm going to just quickly just name this untitled, and we can see what the difference is here. Our 48-bit depth normal map texture is 19.5 megabytes. That's pretty big, but our 8-bit depth is only 6.12 megabytes. You save a lot of data by choosing a lower bit depth. But going back to what we were doing with our ORM texture, again, I would just save this as a PNG image with a color depth of 8. And again, we didn't save any data in the alpha channel, so we can just save this in the RGB sort of format here. And for PNG, I like to turn compression up to 100%. If you're working with a file such as JPG or WebP, you will definitely want to put quality up to 100%. Same thing with WebP, you want to put that quality up to 100%, because JPG and WebP they are lossy compression formats, meaning you're going to lose data if you save out a JPG or WebP file with a quality value lower than 100. But I always like saving my textures out in PNG for multiple reasons, which I will get into in just a little bit. So we can save this out as our ORM texture. You saw earlier I have an ORMD texture. Now what is that? Basically it's the same as ORM, but I packed the displacement texture into the alpha channel. So that's what that D stands for. So let's do that real quick. Let's take the displacement texture and let's take the value and plug that into alpha. And let's save that. You can see it doesn't look like a whole lot has changed, but if we go up here to the display channels drop-down menu and we can change color, you can see it flash just a little bit, but if we take a look at the alpha channel, you can see that our texture is there. And let's go ahead and let's save this out as our ORMD texture. We do want to change this to RGBA since we are storing data in the alpha channel. And let's set compression up to 100% again. And even though our displacement texture was a 16-bit texture, I'm just going to save it as 8-bit. And let's save that out. So let's see what that looks like. Wow, it doesn't look the same as earlier. And it has a much smaller... You take a look here at our ORM texture, the size is 4.9 megabytes, but even though we saved more data in our ORMD texture, it is only half the size of our ORM texture. So what gives? What's the reason why? Well, it is an issue with how we saved out the image. Or more precisely, it is an issue with our node structure here. So let's open this up. Let me clear all these things out of paint.net so I don't have all this clutter. Let's open this up in paint.net and see what's going on. So we look here, let's sample the pixels that we can very obviously see here. So yeah, some funky stuff is going on with the blue channel a little bit, but if we start sampling these opaque pixels, you can see that our data has been completely overwritten. We're not seeing the RGB values that we would be expecting. So we just lost a ton of data. So how do we get this data back? Well, we need to change our node structure here. And what we do is we need to get a color, I think set alpha. Yep, set alpha node. Haven't actually done this in a while, so I couldn't exactly remember what it was, but I remember it now. Instead of plugging our displacement texture into the alpha channel, we can instead plug the displacement into the set alpha. We want to plug it into the alpha slot of the set alpha node. And then we want to take our image and then plug that in there as so. And now you can see it looks quite different. Now for mode, we do want to keep this as apply mask. Now when we render this out, you can see it looks quite a bit different. Now let's save this out as our ORMD texture PNG. There it goes. And let's reload it into paint.net. Now when we start sampling the pixels, you can see the RGB values have been preserved despite the alpha value. So why did that happen before? Well, that is actually a common practice of compression in image formats. So, and this is an issue with another format, which I will show you in just a little bit. But most image file formats are not designed for data storage. They are designed with the intention that the images are going to just be used as a visual medium. So when you have a pixel that reaches a certain opacity, the image format is going to assume that pixel is not going to be seen anyway. So what's the point of storing the RGB values? To get a smaller image format, we can go, okay, this pixel's not going to be seen anyway, so there's no point in storing those values in that pixel. And that is, as you can see, even though we have a PNG format, our values are remaining the same. But, word of warning, WebP is a really awesome image format. But as the name implies, WebP, it is an image format that is meant to be used on web pages, and therefore it is intended to be used as a visual medium. So if a pixel reaches a certain alpha threshold on the WebP format, it is always going to be overwritten with a fully black or fully white pixel rather than what the RGB values are, which sucks because WebP is an excellent format with compression. WebP is supported by the Godot engine, and it kind of sucks that, you know, we can't really rely too much on WebP because of that limitation. But in my opinion, from my tests that I've done, PNG is totally okay. PNG is really good at compression. Not only is it good at compression, but it compresses your files while keeping all of the important data that is in that file. So I would highly recommend just sticking with PNG textures when you are working with the Godot engine. All right, so now we have our channel pack texture, but how do we actually use them in Blender, in software, in game engines? So as before, I dragged in my ORM texture, and because this ORM texture stores the ambient occlusion map, the metalness map, and the roughness map, we don't need these three textures anymore, so we can just delete them. But how do we separate these values in the Blender shader graph? Well, all we need to do is we go to add color, sorry, not color, separate converter, separate color. And here we can separate these values. We can separate, we can do red is ambient occlusion, which we are going to put in our multiply node. Green is roughness, and metalness is blue. As you can see, it didn't look quite the same as before, and that's because we can change the color space to non-color, and that's going to give us a more accurate representation of our textures. So you can see we have the exact same information, the same outcome as before, but instead of 3 textures, we only need this 1 texture, and that greatly optimizes our projects and reduces the amount of textures we need to call. How do we get the alpha value? Let's say we bring in our ORMD texture. How do we get the alpha value? Well, you don't need, if you're just using the alpha value, if you're just packing a texture into the alpha channel, so let's say you have your color map and you don't have an ambient occlusion or metal texture, there isn't any transparency in your color texture, you may just want to pack the roughness texture in the alpha channel of your color texture just for simplicity. So, but how do we get the alpha value? That's very simple. All you need is this little node right here, this little output right here, and that's going to give you the alpha values of your texture. So let's see what that looks like. I'm going to plug in the color into base color, and I'm going to remove all this stuff. But something doesn't look quite right. Why are these areas dark here? They shouldn't be dark. We don't have, if we take a look at our ORM texture, which is identical to our ORMD texture, except the ORMD has an alpha packed channel. If we look at our ORM, we don't have those dark places. So where did this darkness come from? Well, we need to change one thing in this node here. And under here, alpha straight, we need to change this to channel packed. And you can see now we get our values back. And that's this, it's the same concept as I just said before. When you import a texture into Blender, it's going to automatically assume that that texture is just used as a visual format, a visual medium, not for data. And that's what straight is used for. When it doesn't have to load all these values in, it saves on memory, but we want these values loaded in. So that's why we need to set this to channel packed, and that's going to give us our values back. Now, let's say, just for example, I know it's displacement, but let's just say, for example, that alpha stores our roughness. So let's put this into roughness, and now you can see we get our roughness map there. So that's how you would use channel pack textures in Blender. Let's go over to the Godot engine and let's see how we can use channel pack textures there. All right, so here we are in the Godot engine, and let's create a new folder to store our textures. Let's call this metal plates 13. And let's bring in our color map, our normal map, and our ORM map. And let's drag those into our metal plates folder here. Now you can see all of those images have been imported. Let's go ahead and let's bring in, let's make a new 3D scene, and let's get a mesh instance to view our textures. Under the mesh instance 3D here, under inspector, let's just give this a box mesh. All right, now we need to apply our textures onto this box. Well, the first thing I'm going to do is I'm going to go back to our metal plates 13 folder here. I'm going to create a new resource. And since we have an ORM texture, let's make an ORM material 3D. And let's name this metal plates 13 ORM. Let's save that. And then we can, if we go back to our node here, let's change surface material override. Let's load our ORM texture. And you can see nothing changed, but that's because we need to apply our textures to the material. I think the first obvious step is to bring in our color map, our base color map, and we want to plug that into the albedo texture here. So let's go ahead and let's put that into texture, and you can see now our box mesh has our color texture applied. Before we do our ORM texture, let's do our normal map. So we want to go here under the normal map dropdown. Let's change that to enabled, and we want to plug in our texture here. So let's bring in our texture, and we can see there is a bit of difference here. You can see the bump mapping right here take effect, but it is kind of hard to see since we don't have any reflectivity or anything like that, which is what our ORM texture supplies. So let's go to the ORM dropdown and let's bring in our ORM texture. And now you can see, look at that. Looks pretty good to me. Our material, our ORM textures, all of our textures that we've imported now look great. They are successfully applied onto our mesh. But let's say you didn't pack your textures in the ORM format. Then the ORM material here is not going to be very useful. So let's create a new material. Let's change our mesh instance 3D. Let's name that ORM. Now let's bring this out to the side like that. Now let's bring in another mesh instance and let's set this to box mesh again, and let's create another new material. So create new resource, and instead of ORM, let's do standard material 3D. Let's do that, and we'll name this metal plates 13 standard, and let's get our new mesh instance 3D. Let's change surface material override. Let's load our new standard material. Okay, so let's apply our textures onto this new material. So we'll do the same thing with albedo and normal map as before. We'll just load in our color map there. You can see our color map is applied. Let's do the normal map next. We'll enable the normal map. Let's drag in our normal map into the normal map slot. You can see here our normal map is applied. Now, what about our channel packed texture? Instead of having an ORM drop down here in the standard material, we actually have our ORM is actually separated into 3 extra different drop downs, and here you can see we have metallic, roughness, and ambient occlusion. So let's do our ambient occlusion first. We want to enable that, and here let's drag in our channel packed texture. Let's drag that in there, and the ambient occlusion map isn't too obvious, but let's go ahead. Let's keep ambient occlusion open here. Let's do roughness, which is next, and let's bring in our ORM texture. And you can see it doesn't look like anything's changed. Well, that is because we need to change a value here. So under ambient occlusion, roughness, and metallic, when you bring in a texture, you can also specify which channel that texture has been packed to. So ambient occlusion is correct. It is red. We did pack the ambient occlusion map to the red channel, but roughness was packed to the green channel. So we want to change that to green. And now you can see it's looking a lot better. Now let's do the metallic last. Let's bring in our ORM texture there. And again, doesn't look quite right. It looks okay, but the rusty parts are also metallic. We want to change that. So under texture channel, we want to change that to blue since we packed the metalness texture into the blue channel. And now you can see it's looking exactly as we expect it to look. So that's how you can use channel pack textures in the Godot engine. But one more example I will show you is what if you made your own shaders in Godot, but you still want to utilize channel packed textures in your own custom made shaders. Well, let's make a custom shader here. So let's create a new resource and let's choose shader material. And let's do metal, oops, hit enter on accident. Let's name this metal plates 13 shader. And let's rename this mesh instance to standard. And let's create a new box mesh. Let's bring that out. Set this to box mesh. Now let's load in our shader material here. It's going to be shader. Okay, now let's actually let's make a shader. So I'm going to create a new shader here. And this name is totally fine. For the sake of example and simplicity, for better understanding, I'm not going to use a text shader like shader code. I'm going to use visual shader. Now, one important thing to understand about Godot is that shaders and visual shaders are exactly the same, but essentially it depends on if you're writing the shader with code or if you are assembling the shader via nodes on a graph. So for the sake of example, for the sake of simplicity, I'm going to show you the visual shader approach. So let's go ahead and we want this to be spatial. Spatial is for 3D shaders. Canvas item is for 2D and so on and so on. Shader graph, I'm going to do that. Okay, let's create. And let's go here into the shader editor here on the bottom. Let's open up our visual shader graph here. And you get when you're working with visual shaders, you get something very similar to Blender's shader node window. So I think first thing we can do is we can bring in our color map here. Here, we're specifying this as a data source. We can, since this is our color map, we can just set this to color. And let's bring in our color value into albedo. And there you can see our map is applied. But one thing you will notice here is that we're connecting a yellow to a purple input. And that's because yellow refers to a vector 4 versus purple refers to a vector 3. And a texture 2D will output a vector 4 because it's storing 4 different values. You have red, green, blue, and alpha. Versus albedo, albedo doesn't expect the alpha channel. It only expects the red, green, and blue channel. And there, if you had a texture that had alpha transparency, you would take the alpha value here and you would plug that into alpha. But we don't have alpha transparency, So what this does is that this does convert a vector 4 into a vector 3. If you wanted to be a little safer, you would bring in a vector 3 compose node here, and you would take the color values here under the dropdown, red, green, and blue, and here you can see it's outputting a vector 3, and put that into albedo, and you can see it's giving us the same result. So that's kind of a little bit of a safer way to do that. It's unnecessary, but, you know, in case you want to do that for some reason, you can. As I was editing the video, I realized there was something I should have mentioned, and it's a kind of a fun fact, and this is the case with basically every piece of 3D software. So you'll notice that X, Y, and Z are red, green, and blue in that order, X, Y, Z. And that's because, well, in 3D space, we work with three-dimensional vectors. Used to, in previous versions of Godot, when you would have a vector compose node like this, the X here would be red, the yellow would be green, and the Z would be blue. Now, think back to what I said earlier in the video, where, you know, we have red, green, and blue in that order for image textures. That is the reason why X, Y, and Z, respectively, are red, green, and blue. That's not by accident, that is by design. And that is the case with every single piece of 3D software that I know, that even if Y is the horizontal axis and Z is the vertical axis, Y and Z are still green and blue, and X is always red as well. Just a little fun fact. Now, let's bring in our normal map. Now, instead of data, we can set this to normal map, and we should be able to just plug this into normal map as we did with our color map, and you can see our normal map is working. So again, you could convert this into a vector 3 if you wanted to, since we are, you know, putting a vector 4 into a vector 3 slot. Again, unnecessary since it kind of does it automatically, as you can see, but whatever. I'm going to do that for our color map anyway. So now let's bring in our packed texture, our ORM texture. Now we want to keep this as a data source. You already kind of saw how we can do this, but, you know, instead of needing a color separate color node like we did in Blender, we can literally just take these output nodes here. It's already giving us the red channel, so we can take red and we can put that into AO here. We can take green, we can put that into roughness, and we can take blue and put that into metallic. And now you can see we got an identical material here to our two other materials. So this is good if you want to apply effects such as detail maps, and stay tuned on this channel because I will be doing a video on detail maps in the Godot engine in the future. So if you want to learn about detail maps and how to make some really cool effects using detail maps, stay tuned for that video. But I will show you how you can utilize detail maps in this sort of node setup here. And that is one effect that you do need to make your own shaders for. Now, you may be thinking, well, hold on a second. If we take our ORM material here, and there is an area for detail, but this is one way to do detail maps. I don't like this way of doing detail maps. I prefer doing my own custom way of detail maps because I have a lot more control of how I can utilize detail map. That will be the end of this video. I hope this video was very useful to you. Again, this was a video that was geared towards beginners, but hopefully if you are on a more intermediate or advanced level, hopefully this served as a refresher as well. And if you stuck around this long, then I hope you enjoyed the video. And if you did, like and subscribe. I'm going to be making a lot more game development tutorials and videos similar to this one, specifically working in Blender and the Godot engine, which are my softwares of choice. But especially in this RGBA video series, tutorial series, everything you see here is engine agnostic. So all of the concepts apply in Unity and Unreal. And like I said earlier, Unreal, even just like Godot, has out-of-the-box support for ORM pack textures. Stay tuned on the channel. I'm going to be making more videos similar to this one, and if you would like to see those videos, then subscribe, and I will see you then. Take care, everybody.